Hola, ¿cómo les va? Ya estamos por iniciar la keynote del día de hoy. Hoy tenemos a la doctora Brittany Johnson-Matthew. Ella es profesora adjunta del Departamento de Informática de la Universidad George Mason, donde dirige el laboratorio INSPIRE, que por las siglas en inglés significa Investigación y Desarrollo de Prácticas de Software Interdisciplinarias. Recibió su doctorado en Ciencias de la Computación de la Universidad Estatal de Carolina del Norte, después de obtener su licenciatura en Ciencias de la Computación del Colegio de Charleston. Su investigación explora los problemas sociotécnicos relacionados con la productividad de los desarrolladores y el desarrollo y el uso del software, como el apoyo a las herramientas, los entornos de trabajo, la ética y el software para el bien social. Su trabajo es interdisciplinario y transversal con la investigación en ingeniería de software, la interacción persona-ordenador y el aprendizaje automático. Brittany nos grabó su charla, si nosotros podíamos subtitularlas al español, así que yo ahora voy a compartir mi pantalla y voy a hacerle play al video, y después de eso vamos a poder tener la oportunidad de charlar con Brittany, de hacerle preguntas y poder interactuar con ella.
George Mason University. I am both honored and excited to be giving this keynote presentation at the Argentine Conference on Informatics. Today, I'm going to talk to you about an important issue in today's software landscape. What you're seeing on the right side of your screen right now are examples of data-driven software systems that have been built and used to make important decisions. What I'm going to discuss today are the ethical concerns, such as fairness, around these kinds of software systems, and ways we can identify and prevent undesirable, unethical behavior in data-driven software systems.
Data-driven systems, like the ones mentioned in these articles, are built and used to improve how we live our lives and reduce risk and bias. However, in reality, while these systems have good intentions, we often see that they can behave in unexpected and undesirable ways that can have or have had negative impacts on society. Unexpected behavior is not new to software. As we already know, software can have bugs. While we generally want to make sure our software is bug-free, this becomes of more importance when we think about critical software systems. These bugs can have critical outcomes. For example, this is Robert Julian Borchak Williams. Due to a bug in a facial recognition software system used by police in Detroit, Robert was wrongfully arrested and detained for a crime he didn't commit. And this, unfortunately, is just a recent example of the many instances where software used in the criminal justice system have led to unjust outcomes. Consider another recent example pertaining to COVID-19. The pandemic has led to an increased need for efficient, effective healthcare and a decrease in employment. It would seem technology could help with these issues. However, bias in software systems have led to inequitable distribution of support. Yet another example of software where there are ethical concerns is driverless cars driven by AI. While there are bias concerns around integrating AI into our vehicles, there are also safety concerns regarding the ability of self-driving cars to function as expected in the variety of situations it may encounter when on the road. These kinds of unethical outcomes and the potential for others bring into question the ethics of building, disseminating, and using data-driven software systems. This leads to an important question that is AI for everything and everyone? Right now, the answer is we don't know. And an important goal should be to support answering this question. To do so, we first need to think about how we can minimize the potential for unethical and undesirable outcomes. Today, I will talk about one part of the solution, which is providing support to software teams for detecting and preventing unethical outcomes. When thinking about this problem in the context of data-driven software, one important consideration to make is that data-driven software is built using a different process with different and unique concerns in comparison to traditional software development. There have already been numerous studies on the differences between building traditional software systems and building systems that use machine learning. More specifically, while a data-driven pipeline has similar components as traditional software development, such as software design and evaluation, the addition of machine learning models means the addition of steps in the machine learning pipeline, such as model design and evaluation. There are also new concerns when thinking about how the model integrates into the software and how we can validate that this will lead to expected outcomes. Today, I'm going to talk about how we have begun to and could further support the change in process for building ethically sound data-driven software. Much of the work pertaining to building machine learning software has focused on the machine learning pipeline. I'm going to focus this talk on how we can think about support for the bookends of the data-driven software pipeline, starting with the process of defining how we expect software to work with respect to ethical concerns. The first step of any software pipeline is software design. So one might be thinking, why don't we just make data-driven software fair and ethical by design? There are many studies that have explored ethics by design, and this is an important area to make progress in. But there are many other causes of ethical defects, including bias in the underlying dataset, design or implementation bugs, unintended interactions, or even societal phenomena, like the fact that one gender is more likely to wear makeup than another, or that some streets are more well-maintained than others. Software design won't be able to address all these issues alone. What we need are tools that can detect ethical defects in software to inform both software teams and users on how to improve development and use of the software. I'll talk more about this later in the presentation, but I want to point out that ethical concerns like software fairness are just like quality or security. To say that software needs to be secure could mean different things for different domains and in different contexts. The same is true for ethics. Depending on the domain and stakeholders, what is considered ethical can vary. For example, the term fair could take on various definitions, which I will also discuss. But just like quality and security, ethical concerns must be part of the software engineering lifecycle and considered throughout the development pipeline. Which brings us to the next important question to answer, which is how we should think about ethical concerns when defining software requirements. Recent work has suggested a breakdown of ethical concerns in AI to drive improvements to the machine learning pipeline, including concerns such as inconclusive and inscrutable evidence and unfair outcomes. While these may not be exhaustive of all the ethical concerns at the software level, such as safety, these provide a reasonable starting point for concerns that arise when considering the integration of machine learning into software. In this talk, I'm going to focus on unfair outcomes, as this is an area that has been explored in the software community. However, I want to point out that there is opportunity to explore how we can apply these other ethical concerns to how we think about building data-driven software. To start, let's consider this simplified example of a data-driven loan software. Loans input is a loan application. For simplicity, let's say the inputs are income, savings, age, and race. The program's output is either approved or denied. Now, there may be disagreement about what is and is not okay to do. Discrimination is a loaded term, but you and I are likely to agree that it is okay for the loan program to discriminate based on savings or income, but perhaps not with respect to race or age. This presentation isn't about the important questions around what is or isn't okay to discriminate with respect to. Instead, it focuses on the situation where a company and customer have decided that the software should not discriminate with respect to certain information and wants to determine and measure if the software does so. Your first thought might be, why is race even an input to the loan program? Why not omit this information? Then the loan program can't discriminate, right? Unfortunately, prior work has found this is ineffective due to correlations in data. For example, LaTanya Sweeney found that searching for traditionally Black names on Google resulted in a higher likelihood of seeing ads for arrest records. The important thing here is that the query didn't include race or any other sensitive attributes, just the name. Google has fixed this specific problem since then, by the way. But the issue here is correlations between attributes. Without having age or race, the loan program could infer that information from other information provided. In 2016, Amazon used an algorithm to decide where to offer same-day delivery. For Boston, the algorithm decided to deliver everywhere except that one neighborhood in the center, Roxbury. It turns out Roxbury is a predominantly minority neighborhood. Now, you might say that happened by chance, but in city after city, the same thing happened. Amazon got a lot of negative publicity for this and manually overrode the algorithm. But the key observation here is that race was not a part of the input to the algorithm, but in America, race correlates with zip code, and the algorithm found a way to discriminate. Now, we could talk about the underlying data and why that happened, but from a software engineering perspective, this is clearly not a property of the system Amazon wanted. Surely, they would have preferred to have tools to have been able to test the software for such discrimination, and ideally design and build it without discrimination in the first place. The idea of hiding data from the algorithm is called disparate treatment. This is even required by law in some situations. But empirical evidence has shown again and again it's simply not enough. Let's consider another definition of fairness called demographic parity. This definition compares population proportions. In our example, if 35% of green people get a loan, but only 20% of orange people do, the bias, according to demographic parity, is 35 minus 20, or 15%. However, this definition also has problems. In particular, it fails to capture bias against individuals. Let me demonstrate that with an example. Suppose our loan program gives loans to all the orange people in Europe, but to none of the green people there. In Asia, it does the opposite. All the orange people get denied and the green approved. If the number of orange and green people in the two continents are the same, demographic parity says this system has a bias of 0, even though it's clearly discriminating against race based on location. Now, one might say, this is just a matter of defining your sensitive attributes correctly. If race and location were both sensitive here, demographic parity would catch the discrimination. Unfortunately, while this example makes it really easy to see how to separate the groups to catch the bias, prior work on fairness gerrymandering has found that this is not typically obvious or possible. So far, I've talked about 2 different definitions of fairness, but there exist many others. Disparate impact is related to demographic parity, but looks at the ratio instead of the difference in proportions. This definition is commonly used, but also fails to accomplish the goal of individual fairness. Delayed impact captures the notion that seemingly fair decisions today could have vastly unfair consequences down the line for the groups you wish to protect from discrimination. Some other commonly used definitions include predictive equality, equal opportunity, equalized odds, and treatment equality. And the list goes on and on and on. And each may be appropriate in different domains and different contexts. Determining when what metrics are appropriate is an important problem area and still an open problem for explorations. But all the definitions mentioned here suffer from the same problem. None of them would catch the Asia-Europe example I showed earlier. The reason is that these definitions fundamentally measure correlations between sensitive attributes and software behavior. And as we know, correlation does not mean causation. What we really want to know is when sensitive attributes affect software behavior. We want to measure causality, which means in terms of software requirements, we may be able to specify and test for the requirement, for example, that sensitive inputs should not affect software behavior. Whether this is enough or not is an open challenge for our communities to explore, but for today, we're going to focus on this example requirement. So once we have requirements for our software system, what's next? Well, we want to test that these requirements are being met, of course. Our requirement aims at evaluating causality, which is typically difficult to do. But with software, we are actually very lucky. Prior work in software engineering has developed a technique known as causal fairness testing. This starts with the observation that we want to be able to measure when sensitive inputs affect software behavior. Based on this, we can form a hypothesis and test it. Suppose green Brittany fills out a loan application and it gets approved. Well, we have the software, and we can generate a loan application for orange Brittany and run the software on it to see if the outcome is the same or different. If it's different, then since the only difference in the inputs was Brittany's color, we know that color caused the different behavior for this particular input. And we can do this for many inputs to measure how often this happens. Now, those of you with experience in software testing know that it is relatively easy to generate inputs. The hard part is generating the oracle for the test, which specifies what the test is supposed to do if the software is correct. With causal fairness testing, we're again very lucky in that we don't need an oracle. The fact that green and orange Brittany's loan applications should result in the same outcome is our oracle. To test for fairness, we don't need to know which outcome is correct as long as the two outcomes are the same. Now, this doesn't preclude correctness testing. You very well may care about which outcome is correct. But for the sake of fairness testing, only the consistency of outcomes is important. We built a tool called Themis, named after the Greek goddess of fairness, for automatically generating test suites to measure discrimination. Themis works on categorical inputs, which makes it relatively easy to manipulate sensitive attributes, though we and others are working on expanding this idea to other types of attributes. Themis is open source at fairness.cs.umass.edu. Themis allows you to answer questions such as, how much does my software discriminate with respect to specific attributes? And does my software discriminate above some threshold, and against what? For efficiency in generating tests, Themis uses adaptive, confidence-driven sampling to know when to stop generating tests, and sound pruning to reduce the number of tests needed to measure some discrimination. Details on how this works can be found in the paper. Let's talk about the evaluation of Themis and what was found. The evaluation trained 8 open source decision systems on 2 public data sets, the Census Income Dataset and the German Credit Dataset. The evaluation included commonly used decision systems, some of which are designed to avoid bias in learning. All the FAIR-aware algorithms were designed to reduce demographic parity. The goal of the evaluation was to see if Themis can effectively catch bias. The study found, as expected, that demographic parity is not enough. In one example, a decision tree that was trained specifically to optimize gender demographic parity did so, but experienced 0.11 causal discrimination with respect to gender. This means that for 11% of the users, just changing their gender and keeping everything else exactly the same changed their credit label from good to bad, or vice versa. So what's going on here? Well, it's exactly the fairness gerrymandering I mentioned earlier. Machine learning finds a way to manipulate the data to maximize whatever you ask it to maximize. And if your data has bias in it, and you don't explicitly ask it to avoid a particular kind of bias, well, you get bias back. The study also found that optimizing demographic parity can inadvertently introduce other kinds of bias. For example, a system that was trained to optimize gender demographic parity ended up significantly increasing the discrimination against race up to 38%. Again, the observation is that if you don't specify for your system exactly what to enforce, it has no reason to enforce it. This further supports the importance of specifying fairness requirements properly, as you would for any other software property. Finally, the study found that the pruning techniques used were quite effective, reducing the test suite size by 148 times on average for causal testing and over 2,800 times for demographic parity. Once we've found fairness defects, the next step is the sometimes dreaded process of debugging the defective behavior. Causal testing is not only a powerful tool for discrimination detection, but can also be used for finding and understanding any kind of bug. We have a paper in ICSE 2020 on using causal testing to debug. The central idea is that to a developer, seeing 2 nearly identical test inputs and executions, one that passes an oracle and one that fails, can be very useful. Seeing these causal pairs can point to the cause of the defect, supporting the ability to find and remove it. Imagine seeing one buggy execution for an online shopping portal with a large cart full of items and lots of shopper information as input, and this execution results in an error that says illegal purchase. Now you have to hunt down the cause of that error. Now imagine seeing the exact same execution coupled with another one that shows that if everything else is kept the same, except the shopper's birthday is changed to make them over 18 years of age, the execution no longer results in the error. The focus today is on fairness, but if you're interested in how causal testing can support debugging, check out our paper, Causal Testing, Understanding Defects' Root Causes. Now, let's get back to software fairness. Testing goes hand in hand with debugging. Themis not only measures causal discrimination along with others, it also produces causal pairs as evidence of the discrimination. Developers can, in theory, use these pairs to examine their data, perhaps augment the data, or to help understand their system's logic. There have been several papers published building on Themis, looking at improving the efficiency of finding these causal pairs. Much of this work focuses on the machine learning or data level of data-driven software, which is of course an important part of the problem. However, an important area for future work, which myself and others are actively interested in, is the ability to look at debugging these kinds of defects at the software level as well. Up to this point, I've focused on software that has categorical inputs, such as loan applications, where race is listed explicitly. This makes it somewhat easy to modify the sensitive attribute without changing anything else. But there are numerous other complex cases. For example, the attribute of interest might not be explicitly included in the input, or other attributes might correlate with it. What we have done so far is a conservative approach. If Themis says a system causally discriminates, then it definitely does. That's because Themis has found inputs where changing one or more attributes, such as gender or race, directly affects the outcome. But Themis is incomplete. It's possible for a software to discriminate, but Themis not see it. This can happen, for example, if there are correlations between the sensitive attributes of interest and other attributes. But when Themis modifies the sensitive attributes and doesn't modify the others, the discrimination doesn't surface. Here's a simple example. There's a correlation between gender and hair length. Suppose a loan program looks only at hair length to decide whether to approve a loan. Two people of identical hair length, regardless of gender, would either both get the loan or neither get the loan. So Themis would claim no causal discrimination. And Themis is right, kind of. The problem is that when applied to a real population, the loan program in practice will make decisions based on gender. One nice thing about Themis is that the user can define what a sensitive attribute is. Say our software collects zip code, and we know that zip code is correlated with race. We could ask Themis to report on how much discrimination happens with respect to zip code. The challenge here, in an area for future investigation, is knowing these correlations in advance and what they mean for software behavior. It's also possible to overcompensate in the other direction. Themis could project the other attributes using their correlations with the sensitive attribute. Others have done this, and this could catch more bias, but the measurement is no longer sound. That is, it could identify bias in a system that doesn't exhibit it. There's currently ongoing work on improving how machine learning systems deal with correlations between sensitive and non-sensitive attributes. A more challenging problem is handling continuous, semantically complex inputs. Let's consider another example of bias in software. ACLU did a study of Amazon's facial recognition software. Until recently, law enforcement in America was using this specific system. ACLU found that the system discriminated. So what does it mean to discriminate in this context? Facial recognition is a hard problem, and you can't expect the software to be correct every time. But here, ACLU found that when the software did make mistakes, the false matches were disproportionately people of color, including 6 members of the Congressional Black Caucus. This again brings up the important question of if and when we should be using these technologies in practice, given the potential for disproportionate adverse effects, which can go beyond results of a study and into reality of affected people, actual people, as with the example I mentioned earlier regarding Mr. Williams. The measure of bias used in the previous example is a correlation-based measure which compares the number of false positives in each group, not causality. But this is still discrimination and still important to measure. However, this talk is focused on the importance of causality. So what would it even look like to test facial recognition software for causal bias? You'd have to create images of people that are identical in every way, except a sensitive attribute of interest, such as race or gender. Well, researchers at NVIDIA are working on just that. I'm showing here results of again generating images of faces. If you haven't been to thispersondoesnotexist.com, I highly recommend it. It's a great way to lose an hour or more of your life. These faces are incredibly realistic, but they're not of real people. They're generated. The idea is to train from real faces, embedding them in a latent vector space, such that every point in that space can be decoded into a face. You simultaneously train a classifier that tries to decide if the coded face is a real image or a computer-generated one. Taking this adversarial approach, you keep training your encoder and decoder together until they fool the classifier into thinking the generated images are real. So take a close look at these two rows of images. In each row, you look at the images in the middle. There are gradual projections between the leftmost and rightmost images. It's not perfect, but you can clearly see the trajectory. What's happening here is that the leftmost and rightmost faces are points in that latent vector space, and if you draw the line connecting those points, sampling points along that line are the interpolations between the two faces. But there's something kind of strange happening here. Let me give you a moment to see if you can catch it. Did you find it? Well, these two faces are identical. So these two lines in the multidimensional space happen to cross. This is very promising technology, but they're all fake generated faces. Some folks have been working on embedding real faces into this latent vector space to then project real faces. This can lead to changing higher order attributes of faces, such as gender or race. But that's hard work and still a work in progress. There are many people working on a similar problem in the area of natural language processing. There, the problem is called style transfer. There are some promising results, but again, we're not there yet. So far, I've spoken mostly about handling software fairness at the software level or using software engineering techniques. I want to touch on some work that's been done at the machine learning level with respect to providing fairness guarantees in classifiers. So, how would you build a machine learning classifier that can train on data without knowing if that data has bias and produce a classifier that can guarantee that on unseen data it would satisfy a fairness property of your choice? Well, there exists an approach called the Seldonian framework for designing machine learning algorithms. With this approach, the user specifies a fairness definition. The available data is split into three sets: a training set, a testing set, and a safety set. The classifiers are trained on the training set. The testing set is used to produce a classifier that is likely to satisfy the fairness definition the user provided. Once the best guess classifier is produced, the safety set is used once and only once to see if the fairness property holds. Now, here's the important part. For this technique, or any fairness guaranteeing approach to work, it has to be able to say, I can't do that. This approach does just that. This is an important step to being able to answer the question mentioned at the beginning of this talk, which was, should I even use AI in this context or for this problem? To read more about this work, check out the publication in the December 2019 issue of Science. Another important area that I want to highlight is that while it's important to explore interventions throughout this pipeline, what we really need to think about is what do teams really need when building data-driven software? And more importantly, what really works in practice? I would like to thank the sponsors of the work I've done in this space so far, as well as the large group of amazing collaborators I've had the privilege of working with and continue to work with on ethical software development problems. I want to particularly highlight Yuri Brun, who got me involved in this important effort and helped me put together this keynote presentation.
I hope my talk today has demonstrated the importance of ethical concerns like fairness in data-driven software, and that improvements to software engineering practice can help solve these kinds of problems. I also hope this talk has encouraged you to work towards solutions to these important research challenges. I want to thank you all for your time and the organizing committee for the opportunity to give this keynote address, and I look forward to all the new and exciting results from the research community. Thank you.
I'm really concerned about how we decide how to use AI to several problems or issues. I'm a teacher, I'm a professor, so education is one of the things that I really care about. You show some issue with facial recognition, and we see some software because of COVID that use facial recognition and other stuff to see if students are cheating or not. So I don't know if you have an answer for this, but I always wonder myself how some person can come up with that idea, right? Because it's how you are going to do that, but that happens. So I understand the technical, we need to develop this kind of tool that you show us and FEMIS, but in the other hand, how we perhaps teach our developers about how to think about to say, hey, we can do that, or we still shouldn't do that. What is your thought about that?
Yeah, and so I think for me at least, the question of like, who thought of this? Like, who thought this would be a great use for technology, right? Especially in the classrooms. I wasn't aware that was a thing. And I think you could see similar implications, right, in that environment where you might have certain students that don't get picked up, or students that are confused for other students. And so then you as the professor have the extra work of figuring out what actually really happened there. So I think that the problem is multifaceted in that it's going to require more than just even what I talked about today, right? Like getting software teams to agree that, yes, we should care about this, and there are certain things that we can or should be doing. It definitely goes beyond that. And I think that it goes, for example, in software companies or engineering companies, it's at an organizational level. There are societal problems that would still need to be addressed. And as I kind of alluded to in the presentation here, the context beyond just, is it used in criminal justice or healthcare, it's important, right? It's not just that, but is it in the US? Is it in South America? Is it in Europe? Is it in, right? And those things are going to make a difference as well. So I think awareness is step one. I think it's important that software teams are doing things to mitigate these types of problems, or at least be aware of them, to, again, be able to ask themselves, should I be doing this? And if not, is there another solution that I could explore that might be more ethical or sound? But at the end of the day, I think there's a lot of work to be done in different silos. And I think the tech community can be one of those to make some really important change.
Okay, thanks.
Of course.
I don't know, Mariano or Rosita, if you have some question or comments. I have more, but
yeah, definitely open to questions, comments. To me, as conversational or not as possible. I think again, this is a very important but new research area. So there are things that are happening quickly, and a lot of open questions and problems for sure.
Yeah, I also like a lot about the talk, how you can handle these different data that you have, and how can some data hide discrimination. I love your call for action about to know this correlation, because some of them we know from history. They're like historical, we know that this happens, but how we can actually contribute. I mean, I always think about diversity in teams, because my experience, it is different to Rosita or Mariano or yours. Sometimes how we can be aware of that kind of discrimination that can be on the data, and perhaps diverse team can help to bring awareness about that. And then we can.
That's a fantastic, yes. I was going to say, I think that's a fantastic point that maybe isn't often talked about together, in the fact that just by having different perspectives at the table, that by default is going to make some difference. Is it going to fix all the problems? Of course not. But I think it's an important step to realizing that, you know, and I was at an event recently where I had a conversation with a gentleman in the audience where he legit did not understand my perspective or the perspective. So I don't know how many of you may have seen the Coded Bias documentary film.
Yes, yes.
He legit did not understand what the problem was that the documentary was trying to outline. He felt that technology would actually make things more fair and level the playing field, as opposed to, right? So I think that the awareness problem is a real one, and making sure that the conversations are happening. And I feel as if I were not there as a person of color who can directly relate to the types of problems that, you know, we see happening, maybe that conversation never happened, right? Maybe there was never someone to help him to understand, or to at least give him the perspective, you know, that this is a real problem that has real effects on real people. So it's a tough problem, but I think just by having us there at the table, having those conversations, it's a start.
Brittany, as a professor, how do you think we have to include this kind of discussion in the formation of engineers, right? Computer science engineers?
I think
where?
Fantastic and important question. I have another example from the same event that you know, kind of highlights how important this is. So one of the questions that we got at this event was from a student, an engineering student. He was like, so I don't understand, what am I supposed to be doing about this, right? Like, as an engineer, I want to build things. Like, that is what I came here to do. I want to build things. I want to make cool. I want to make advances in technology. How am I supposed to reason about this, right? Did I pick the wrong field to go into? You know, and these are important questions, right? We don't want to discourage people from you know, being in technology because they feel like they now have to have a bleeding heart. That's not what we're asking, right? I think it's important to think about how can we, similar to how we teach, like in the presentation, security, right? If that's an important part of how we teach and what we teach when we talk about programming, writing software, building systems, right? And so I think the important thing to do is to think about how can we mirror these kinds of problems like fairness as we have other concerns that we've seemed to be able to find ways to integrate and get people to care about without feeling like it's an unnecessary burden, or even not their responsibility, right? That it should be somebody else thinking about those things. But it's an open question for sure.
Yeah, Brittany, thank you very much for your talk. It was great. I have a. Do you think there is an undecidability issue here? That is, we are going to go looking for fairness and never getting it, and
you know, and unfortunately the answer is I don't know. I hope not, right? But it could very well be that, you know, we don't get enough interest. And again, I think the interest is there, and there are people that are trying to solve the problem. I think, is there genuine interest in that people are actually wanting to really solve this problem? I think that's the big question mark, which makes it kind of hard to know if this will ever be, if the research will ever be reality, right? So that there's a lot of research happening in the space. There's a lot of fairness interventions that are coming into various venues and conferences, but will that ever translate into practice? And if so, will it ever actually have the effects that we would like to see? And that's some of the research that I hope to do in my lab, is to actually be able to explore the potential for example, all of these different fairness interventions that are coming out in research to actually make that effect on practice, which is an important step, obviously, to actually seeing that change. So unfortunately, another one of the I don't know answers, but I'm hopeful that, between the research that my lab does and collaborators that I work with and others that are in the field, I hope that we can work to translate that into practice. Great question.
Well, I don't see any more questions or comments on YouTube. I don't know if we have Mariano, Rosita, if we have another one.
I don't have, no.
Okay.
And I do want to put out there, I'm happy to field any offline questions if folks, go look at some of the work or find that they have delayed questions or even feedback that they'd like to provide. I'm very much happy to receive that via email at any point in time. So I want to put that out there as well.
Okay, awesome. Brittany, thank you so much again for your time, for being here, and for saying yes. It is an honor for us to having you here with this topic.
It was an honor to be here. I'm really excited that you reached out, and I'm glad that it all worked out.
Okay, well, thank you so much. And we, as I say, we are really happy and we're really grateful that you're here with this topic. I'm going to switch to Spanish now. So
sounds good.
Thank you very much.
Thank you guys
Thank
so
you.
much.
Thanks, Brittany.